Hi. So in the last video, we talked about large margins and how they're associated with small overfitting. So I think it's worthwhile to try to think about this a little bit more to really understand what these large margins mean. Okay, so why are large margins good? On examples with large margin, as we said, the prediction is stable. Okay, so prediction is independent of small changes in the training set. So we're pretty confident that we're going to make that prediction even if we got a different training set. And that's what we mean by confidence. In other words, if we make small changes to the training set, it's not going to cause the prediction to change. And so we can predict with confidence. Now, important to realize that this confidence is very different from when you say, oh, the probability that something is going to happen is close to 0 or is close to 1. Like I'm 99% sure that this is going to happen, or I'm 99% sure that it's not going to happen. This is different than that because there you're talking about what's the true probability of given what you know. This has more to do with the stability of the classifier. Okay, so based on my experience so far, I'm going to say that this is going to be a 1. Now, the actual probability that it's a 1 might be just 55%. But the best prediction for me, I'm sure, is 1. So this kind of thing occurs a lot in various parts of life, but maybe the most vivid examples are in sport. So in sport, a lot of being a good player, what it means is that you can predict what the adversary, what the person that you're playing against is going to do. Okay, so here's an Olympic level player playing ping pong. And as you see, his hand is below the table so that the other player cannot see it. So it's harder for the other player to know what exactly he's doing. And one of the things that you're trying to predict is whether this is backspin or a topspin. Okay, so there are two spins. There are more than two, but let's concentrate on these two. And those depend on whether you're hitting the ball going down or you're hitting the ball going up. Okay, and that spin determines a lot in terms of the response. If you know what the spin is, then you have a particular way that you're going to answer. You're going to answer this way you're going to answer up for backspin and down for topspin. Okay. So to respond correctly, we need to predict whether the ball has backspin or topspin. And by the time that the other player is actually hitting the ball, that might be too late. And we might not actually be able to see how he's hitting the ball. So what we do is we predict from a variation of other information like body posture, experience with that particular adversary, just knowing what he did in the last few things. So if he had backspin, we expect now topspin, right? We expect him to go to the other one. So all of this information comes into the player's head, and somehow he makes a prediction, okay, this is going to be a topspin or this is going to be a backspin. The point of it is that your reaction is going to be completely determined about whether you're going to think it's a topspin or a backspin, right? So it doesn't really help you to basically say, oh, it is 0.7% or 70% that it's going to be a topspin. You have to decide on one of the two responses in order to basically not lose that game. So you're not really confident in the sense of you are 100% sure that this is a topspin. It's just that based on your previous experience, you know that you believe that you have a probability more to hit it with as if it was a backspin or as if it was a topspin. Okay, so the prediction has to be correct more often than incorrect. You don't have to be really correct all the time, but you have to take a particular action each time. So that's the difference between being sure that the ball is going to come in a particular way and being sure that the best thing for you to do is pretend that the ball is coming this way. So this brings us to an important partitioning of the classification error into two or three sources of error. So the first source is the Bayes error. That's basically the best error that even if you knew everything about the problem, you would suffer. So if you remember in the generative setup, we are trying to learn what are the distributions. And so suppose that you knew the distributions, you still would have to suffer some error because the distributions of the different classes have an overlap, and you basically have to suffer some error when you're in the overlap region. So that's the Bayes error. The next error is the model bias. So the Bayes rule has some complicated shape. We don't even know necessarily what it is. But in order to estimate it, we need to use a restricted set of models. And so if we restrict the set too much, we get what is called model bias, right? So the model cannot represent the true distribution, and therefore there is an additional error that we suffer. And the third is data variation, right? Because we're actually fitting our model to a sample of the data, not to the true distribution. And therefore, if our amount of data that we have is small and the flexibility of the model class is large, then we're going to have a big difference between training set and test set error. Okay, so these are the three types. This one you cannot really do anything about, but you can trade off model bias for data variation. Okay, so you can, by making the model more flexible, you can decrease the model bias, but by making it more flexible, you can increase the data variation. So that is what's called the bias variance dilemma. So here are a few ways for reducing the data variation for classifiers. So one of them is model selection. You decide how many parameters you want in the model. So that's, for instance, how many levels I want in the decision tree. Weight decay is a method used a lot when you use gradient descent to push the parameters, push the weights so that they're small. Okay, by pushing them to be small, you are decreasing the representation power of the classifier. Margins is what we were talking about. So if you have something that is basically a sum of dimensions or simple rules, you can look at the margin, and the margin distribution will basically tell you whether you are confident on most of your predictions or not so confident. And finally, bagging is when you just randomize your choices of training data and then take the majority. And that also reduces data variation. So what are the trade-offs? So weight decay and reducing the number of parameters decrease the data variation, but they increase the model bias. Okay, so that's the bias variance dilemma. Bagging is better than that. It decreases the data variation, but without significantly increasing the model bias. Okay, so it basically allows the model to be complex, but it fights variation using averaging. And boosting, you can say, decrease both variation and model bias. So boosting does two things. It both makes the model more powerful, so you have less model bias, and it also uses margins to decrease variance or variation. So that is it for the explanations and the theory about boosting. And next, I'm going to tell you about applications of boosting. See you then.